Hello students, how are you? I hope all of you are fine at your home. Now, in this video we are going to discuss how to represent various positive integers in different forms. So for that, first we'll consider question number 1. So here, we have to show that every positive even integer is in the form of 2 cubes, and every positive odd integer is in the form of 2 cubes plus 1, where q is some integer. Done? So here we have to consider positive even integer as well as positive odd integer. Positive even integer is always in the form of 2 into cube, where positive odd integer is always in the form of 2 cube plus 1. So let's say a is some positive integer. So this a can be positive odd integer, or this a can be positive even integer. Done? So a is one general positive integer. Now we have to represent this positive even integer as well as positive odd integer in the form of 2 cube as well as 2 cube plus 1. So now we will divide this positive integer a by 2. So now if we divide this a by 2 by using Euclid's division Lemma, so we can say after the division of these two numbers we will get 1% q and some remainder r. So here 2q into q is twice of q. So as a process of this long division, we are getting two positive integers q and r. So by using Euclid's division Lemma, we can say that this positive integer a can be written as product of this divisor and quotient. It is 2q plus this remainder r. Done? So this is Euclid's division lemma, which says that this remainder r is always greater than or equal to 0, and it is always less than this divisor. Done? In this long division process, this remainder r will always greater than or equal to 0, and it will be always less than this 2. So here the different values of r, we can take different values of r. R can be 0, it can be 1, or it cannot be greater than 2. So possible values of r are 0 and 1. Done? So here we can replace this r with two possible values on dividing this number a by 2. And therefore we can write this positive integer a as a 2q plus 0, or a is 2q plus 1. Done? 2q plus 0 is nothing but the 2q, and this one is 2q plus 1. Now here the factors of this number are 2 into q, and that means this is even positive integer. This is even positive integer, and this is 2q plus 1, adding 1 into even. So this is nothing but the odd positive integer. Here students, in short, we can say this positive integer a can be represented in form of 2q or 2q plus 1. This 2q is nothing but the even positive integers. So every positive even integer is in the form of 2q, where every positive odd integer, this is odd positive integer. So positive odd integer is always be represented in form of 2q plus 1. Clear friends? So this is how you can solve this question. one more method is there to prove this sum. Done. So for that यहाँ पर लिख देते हैं. So let's say even positive integer. So which are the even positive integers? So even positive integers. Even positive integers are 2, 4, 6, 8, 10 up to infinite. These are the even positive integers. Odd positive integers. Odd positive integers. Odd positive integers are 1, 3, 5, 7, 9, 11. Done. Now, what you have to prove? We have to prove even positive integers are always in the form of 2 into q. These odd positive integers are always in the form of 2q plus 1. So now, we are dividing these even positive integers by 2. Done, because we require form 2q as well as 2q plus 1. So dividing this number with 2. So 2 divided by 2. So 2 ones are 2. Remainder is 0. Now divide this 4 with 2. So dividing 4 with 2. 2 2s are 4. Remainder 0. Dividing this 6 with 2. 2 3s are 6. Remainder is 0. Dividing this 8 by 2. 2 4s are 8. Remainder is 0. Then dividing 10 by 2. With the 2 5s are 10. Remainder 0. So here, by using Euclid's division lemma, by using Euclid's division lemma, we can represent this each and every even positive integers as a product of this divisor and quotient plus remainder. So it's a 2 into 1 plus 0. This 4 can be written as 4 equal to 2 into 2 plus 0. 6 can be written as 2 into 3 plus 0. This 8 can be written as 2 into 4 plus 0. 8 equal to 2 into 4 plus 0. This 10 equal to 2 into 5 plus 0. Done. So here, these 2, 4, 6, 8 and 10, by using this Euclid's division lemma, we can say that these even positive integers, each and every even positive integers are in the form of 2. 2 is common. 2 into q, where q is some integer. We can take q as a 1, 2, 3, 4, 5, any positive integer for any integer plus 0, that is equal to twice of q. Done. So this is how you can show even positive integers can be represented in the form of 2 into q. Clear? So here we have proved that a is some positive integer, even integer can be written in the form of 2 into q. Now we will try to prove these odd positive integers are always in the form of 2q plus 1. 2q plus 1. You can use either of the one method to prove this question. Okay. Now, odd positive integers. Odd positive integers are 1, 3, 5, 7, 9, 11. So let's start with 1. Dividing 1 with 2. So here, it's a 2 zeros are 0. 1. Then dividing 3 with 2. 2 ones are 2. Remainder 1. Dividing 5. Dividing 5 with 2. 2 2s are 4. Remainder 1. Dividing 7 by 2. 2 3s are 6. Remainder 1. So here we can say this 1 is nothing but the 2 into 0 plus 1 by using Euclid's division lemma. This 3 is nothing but the dividend equal to divisor into quotient plus remainder. It's a 2 into 1 plus 1. We can write this 5 as a 2 into 2 plus 1. You can also write this 7 as a 2 into 3 plus 1. These are the odd positive integers. Positive integers. So we can say any odd positive integer. Any odd positive integer can be written in the form of 2. 2 is common. 2 into q, where q is some positive integer. Q is any integer. We are given q is some integer. So 2q plus 1. Clear plus? So there are two ways by which we can do this question number 1. Clear friends? Now pause this video and note it down. Okay, now next question. Here we have to prove that any positive odd integer, again we are given positive odd integer is in the form of 4q plus 1 or 4q plus 3, which is same as previous question. In previous question we have proved that any positive odd integer is in the form of 2q plus 1. We have proved that positive odd integer is in the form of 2q plus 1, where we have divided our required integer by using 2. Now here we have to prove this for this positive integer in the form of 4q plus 1 or 4q plus 3. So let's start it for assumption. So let positive integer require positive odd integer is a. This is required positive odd integer. Now a can be represented in form of 4q plus 1 or 4q plus 3 that we have to prove. So now we are dividing this a by 4 because here we are given 4q plus 1 or 4q plus 3. So now we are dividing our positive odd integer a by 4. So by using long division we are getting two integers q and r as a quotient and remainder. This will be equal to 4q. So after long division of a and 4, we are getting another two positive integers q and r. So by using Euclid's division lemma, we can say that this positive odd integer a is nothing but the 4q plus r, where value of r can be greater than or equal to 0. But it will be always less than this divisor, which is 4. So here possible values of r are 0, 1, 2 and 3. Total 4 possible values of r can be there. Remainder r cannot be greater than this 4. R is some positive integer. So possible values of r are 0, 1, 2 and 3. So here we can write this a as n. If you take r equal to 0, so a is nothing but the 4q. We can write this a as n 4q plus 1 if value of r is 1. If r is 2, we can write this a as n 4q plus 2. And if r take 3, then a is 4q plus 3. Done? So here a is any integer. So here 4q is 2 into 2q, which is even. A is even. So here this 4q plus 1 is nothing but the odd positive integer. Same way this a is 4q plus 2. So here we can take 2 common. So it's a 2q plus 1. So again this a is even number. And here if we add 4q plus 3, which is nothing but the odd positive integers. So here this a is odd positive integers for a equal to 4q plus 1 or 4q plus 3. So any positive odd integer can be represented in form of 4q plus 1 or 4q plus 3. And here you have to make the correction. Let any positive integer is a Done? Then here we can write that any positive integer in form of 4q, then it will be even number. If a is written in the form of 4q plus 1, then it is odd number. 4q plus 2, 1 factor is 2, so it's an even number. And 4q plus 3, so this is nothing but the odd number. Done? This is first method. Or we can prove this one by using long division process. So here you have to prove positive odd integers. So let's say positive odd integers are positive odd integers. So positive odd integers are odd integers 1, 3, 5, 7, 9, 11, 13, 15, 17 up to infinite. These are the positive odd integers. Let's start with 1. If you divide 1 with 4, so you are getting 4 zeros are 0. So 1. Then divide 3 by 4. 4 zeros are 0. So remainder is 3. Then we take 5. Divide by 4. 4 ones are 4. Remainder is 1. Then divide 7. 7 by 4. 4 ones are 4. So remainder is 3. Then 9. Divide 9 by 4. 4 2s are 8. Remainder 1. Divide 11 by 4. 4 2s are 8. Remainder is 3. Divide 13 by 4. 4 3s are 12. Remainder 1. Done? So it will be goes infinitely. So now we can write by using Euclid's division lemma. So what we can write by using Euclid's division lemma? This dividend can be written as product of this divisor and quotient plus remainder. So 1 can be written as 4 into 0 plus 1. 4 into 0 plus 1. By same way, this 3 can be written as product of this 4 into 0 plus 3. Same way, 5 can be written as 4 into 1 plus 1. This 7 can be written as 4 into 1 plus 3. 9 can be written as 4 to 8 plus 1. 4 multiplied by 2 plus 1. 11 can be written as 4 to 8 plus 3. 13 is product of 4 with 3 plus 1. Done? So here we can see this 1, 3, 5, 7, 9, 11, 13 are the positive odd integers, and these positive odd integers are positive odd integers. These all positive odd integers are in the form of, check it, they are all in the form of 4 multiplied by some integer. 4 multiplied by some integer. Let's say 4 into q, where q is some integer. 4 multiplied by q, where q is some integer. So it's a 4q plus 1, or they are in the form of 4q plus 3. This is 4q plus 1, this is 4q plus 3, this is 4q plus 1, this is 4q plus 3. Done? So here we can say that all positive odd integers are in the form of 4q plus 1 or 4q plus 3, where q is some positive integer. Done? Here q is quotient. And here this q is nothing but the some integer. Clear friends? So now pause this video and note it down.
Okay friends, now question number 3. Next question. Now here you have to prove that any positive odd integer is in the form of 6q plus 1, 6q plus 3 or 6q plus 5. In question number 1, we have proved that positive odd integer is in the form of 2q plus 1. Done. Then we have proved that positive odd integer is in the form of 4q plus 1 or 4q plus 3. Now we have to prove that any positive odd integer is in the form of 6q plus 1, 6q plus 3 or 6q plus 5. Done? So all the questions are of same method. So now we'll try to prove this one. So let's say any positive odd integer, let a be any positive integer. Let a is any positive integer. Let a is any positive integer. So now we are dividing a with 6 because we required 6q plus 1, 6q plus 3 or 6q plus 5 form. So now we are dividing our positive integer a by 6. क्वेश्चन नंबर 1 हम डिवाइड कर रहे थे 2 से बिकॉज वी रिक्वायर्ड 2q प्लस 1 फॉर्म. क्वेश्चन नंबर 2 हम डिवाइड कर रहे थे 4 से बिकॉज वी रिक्वायर 4q प्लस 1 एंड 4q प्लस 3 फॉर्म ऑफ एनी पॉजिटिव ऑड इंटीजर. नाउ एनी पॉजिटिव ऑड इंटीजर इज इन द फॉर्म ऑफ 6q प्लस 1 और 6q प्लस 3 और 6q प्लस 5. तो 6q के फॉर्म में चाहिए. सो नाउ वी आर डिवाइडिंग दिस नंबर विथ 6. सिंपल. सो नाउ dividing a with 6, long division process. So according to Euclid's division lemma, we are getting two more positive integers q and r. So 6q, 6 into q, that is 6q. So we are getting r as a remainder. Done. So by using Euclid's division lemma, we can say by Euclid's division, by using Euclid's division lemma, what we can say? We can say a is equal to 6 into q plus r, where r is the remainder which is 0 less than or equal to r less than 6. Remainder r cannot be greater than 6. Done. So it can be 0, 1, 2, 3 up to 5. So possible values of remainder r are 0 हो सकती है, 1, 2, 3, 4 and 5. Total 5 possible values of r are there. So now we can say positive integer a is nothing but the 6q plus 0 when r is 0, or a can be 6q plus 1 when r is 1, or a can be 6q plus 2 when r is 2. A is 6q plus 3 when r is 3, or a can be 6q plus 4 when r is 4, as well as a can be 6q plus 5 when r is 5. These are the total 5 possibilities for r. Now here this a equal to 6q is nothing but the multiple of 2. This a equal to 6q is nothing but the multiple of 2. So any number which is multiple of 2 is even number, so here a is even number, this a is even number. Now we have to prove it for the odd number. So this is even number, 6q is the even number. If we add 1, so plus 1, so this is nothing but the odd number, this is nothing but the odd number. So here for this case a is positive odd integer. 6q plus 2, here we can take 2 common, so it's a 3q plus 1. So this is even number. तो even number हमारे कुछ काम का नहीं है ना, हमें तो रिप्रेजेंट करना है odd number को. So 6q plus 3, so 6q plus 3, this is odd number. Now for this one we can take 2 common, so it's a 3q plus 2 which is even number, and 6q plus 5 is the odd number. So here for these 3 cases a is some positive odd integer. So therefore we can write positive odd integer. Positive odd integers are always in the form of which form? 6q plus 1, 6q plus 1, or they are in the form of 6q plus 3, 6q plus 3, or they are in the form of 6q plus 5, 6q plus 5. So any positive odd integer can be written as 6q plus 1, 6q plus 3 and 6q plus 5. Clear students? So this is first method. We can also prove this one by using long division process, है ना, डिवीजन करेंगे और प्रूव करेंगे. So let me prove it over here, है ना. So which are the positive odd integers, है ना. This one is odd, second part, or we can say second method. So we can write positive odd integers. Positive odd integers. Positive odd integers are कौन कौन से होंगे? 1, 3, 5, 7, 9, 11, 13, 15, 17. These are the positive odd integers. Let's divide this number by 6. By 6, है ना, because we require 6 plus 1 form, 6 plus 3 form, 6 plus 5. So here we have to divide this positive odd integers by 6, है ना. प्रीवियस सम में हम 4 से डिवाइड कर रहे थे जब हमें रिक्वायरमेंट थी 4q plus 1 और 4q plus 3 की. उसके पहले वाले सम में क्वेश्चन नंबर 1 में हम डिवाइड कर रहे थे 2 से, बिकॉज वहाँ पर हमें रिक्वायरमेंट थी 2q plus 1 फॉर्म की. यहाँ पर रिक्वायरमेंट है 6q plus 1, तो 6 से डिवाइड करेंगे. सो व्हाट इज़ द लॉन्ग डिवीजन? 1 cannot be divided with 6, so it's a 0. So here remainder is 1. Then we take 3. 3 cannot be divided with 0, so it's a 0. Remainder is 3. Then we will divide 5 with 6. Cannot be divided, so remainder is 5. Then we divide 7 with 6. It's a 6 1s are 6. Remainder is 1. Then we divide 9 with 6. 6 1s are 6. Remainder is 3. Then 11. 6 1s are 6. Remainder is 5. देखो 1 3 5 1 3 5 कंटिन्यूस रिमाइंडर आ रही है. देन विल कंसिडर 13 नंबर डिवाइडेड बाय 6. 6 2s are 12. रिमाइंडर इज 1. टेक 15. 6 2s are 12. रिमाइंडर इज 3. 17 डिवाइड बाय 6. 6 2s are 12. Remainder is 5. Done. So now we are applying Euclid's division lemma, है ना. इसको नोट डाउन कर लो. So by using Euclid's division lemma, what we can write? By Euclid's division lemma, what we can say? 1 is equal to 6 into 0 plus 1. This 3 is equal to 6 into 0 plus 3. This 5 is equal to 6 into 0 plus 5. 7 is equal to 6 into 1 plus 1. 9 is equal to 6 into 1 plus 3. This 11 is equal to 6 into 1 plus 5. 13 can be written as 6 into 2 plus 1. 15 is 6 into 2 plus 3. And 17 is 6 into 2 plus 5. Continue. Done. So here we can say these positive odd integers 1 7 13 are written as 6 common. 6q plus 1, where q is some integer, or it can be written as 6q plus 3, where q is some integer, or these positive odd integers can be written as 6q plus 5, where q is some positive odd integer. Clear, students? So this is how you can prove any positive odd integers is in the form of 6q plus 1 or 6q plus 3 or 6q plus 5. Done. Now pause this video and note it down.